Oh, yeah, PDF. Whoops. How close is the success? I've already got a date. That's next Tuesday. Right. Is it just me, or like have the recent units been pretty short? Which one are we on? Oh, we're on 5. Is it? Okay. You ever talk to me so late? Why not, huh? Have a good chat to your old teacher. You don't even say good morning or anything.
I thought we just said blue.
So you and I are gonna go talk to Mr. Sheldon about, has he emailed you back? Is it due Thursday, this Thursday or next Thursday? Alright, that's good. Did you send it to the right email?
Yeah.
Did you send it from your school email? I hate people that don't respond to our emails every freaking week.
His picture pops up, I typed his name and stuff, I just I got it from the website.
I don't know. There's no way he'd give us like a bad grade. He'd find some other, it'd be like last time. Oh, I don't know what else we do. There's literally nothing.
There are two things to turn in this morning. You didn't give them to me in Google Classroom. It's a little easier to turn them in now before everybody else gets here. But I guess you have a couple minutes up here. Oh, Leah, we've got new seats. I'm sorry. I forgot you've been gone. You are now in number 24. Be at the end of this row. Sorry. If you guys just came in, make sure that you see that there's 2 assignments to turn in this morning, unless you gave them to me in Google Classroom. So if I don't have those yet, you need to make sure your name's on those during the minute of silence, so we can move on then.
Morning, Gateville High School. It is Tuesday, October 29th, 2024. Please join me in a minute of silence. Thank you very much. Will you please stand as you and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Okay, last call. Any more assignments? 40, 41? 41 was the 8-9 question book assignment. 40 was the notes and practice on first derivative test. Okay, so we are going to continue with a little bit of what we did last class at the end of class today, or in the middle of class today. But first, I need to move you along to the next topic. So in this unit, just a 30-second reminder of what we've done since your first, not the first, but your most recent test. We talked about what critical numbers were and how to find them. We talked about how critical numbers are the only place where a graph might change direction. So if you can find the critical numbers, then you can test around the critical numbers in the first derivative, because when the first derivative is positive, you know your function's increasing. When your first derivative is negative, you know your function's decreasing. And that's enough to be able to answer questions about increasing and decreasing segments. So we practice that quite a bit. And then if you can see where it's increasing, decreasing, you can also see where there's relative maxes and relative mins, which is the first derivative test. Then the next thing we did last class that we started on, and what I'm going to have you finish up today, is extreme value theorem. So that one was where, if you want to know not just the relative maxes and mins, but the absolute max and min, EVT, or extreme value theorem, helps you do that by telling you to do that through a candidates test. So you test the endpoints, you test all the critical numbers, the absolute max and absolute min have to be at one of those locations. So I think you guys only have like 6 or 7 questions left on this from last time, so that'll be pretty short. But along the same lines, something different, but along the same lines, is we're still doing some function analysis. So not just about relative max and mins, not just about points, not just about increasing, decreasing, but now just a different aspect of the graphs, which is something called concavity. So what is concavity? Well, honestly, I don't know if y'all still do this in Algebra 2. It's been so long since I've taught it. But we used to ask concavity questions, but we always gave the graph. So if a graph opens up, it's referred to as concave upward. If it opens down, it's referred to as concave downward. Okay, if f is concave up, like this example here, if it's concave up, then what do we know about the first derivative?
It goes from negative to positive.
No, but that's pretty close though. So actually, let's go down here. Let's do this part first, and then I can make this make more sense. Right here, the part you actually need to memorize. When the second derivative is positive, that's when it is concave up. And the way you're supposed to know information about the second derivative, given information about the first derivative, is use the same thing that I've said 1,000 times this year. Derivative just means slope. The slope of f prime is how you get information about f double prime. The slope of the derivative is like the derivative of the derivatives. Derivative still means slope. So when this guy is increasing, that means his slope is positive, which means his derivative is positive, and the derivative of the first derivative is the second derivative. So when the first derivative is increasing, that's the same as when the second derivative is positive. Okay, and then you could probably guess this stuff, but when the second derivative is negative is how we know it is concave down. And if you're only given information about the first derivative, you've got to think about the way I can take the first derivative and get information about the second derivative is slope or derivative, same thing. So if f prime is decreasing, that means his slope is negative, which means his derivative is negative. And if the derivative of the derivative is negative, the second derivative is negative, and then it's concave down. So you need to understand that when f prime is decreasing, that's the same as the second derivative being negative. So within this, we can do a quick little example here and see some concave up and concave down. So like during this time, a graph can have multiple segments of concave up, where it's opening upwards. A graph could have multiple segments of it opening down, concave downward. And in just a second, we're going to talk about inflection points. An inflection point is where the concavity changes, where it's switching from concave up to concave down, or concave down to concave up. That is what's referred to as a point of inflection. Okay, so if we wanted to figure out, and you will have, there's no surprise about this, I'm not giving you any real unfair information here, but you're going to have a test question that says find where it's concave up or concave down and or both of some random function, and you don't have a calculator. Well, in your head, the part you have to have memorized is these two. Well, if the second derivative is positive, I know it's concave up. If the second derivative is negative, I know it's concave down. At the very least, we know we need the second derivative. So you got to take the first derivative just so you can take the second derivative. Of course, sometimes that's messier and a bigger pain, but this one was not too bad. Now, this is very easy to get mixed up with the first derivative test and critical numbers test stuff. So make sure you listen carefully, because the sooner you get this straightened out, the easier you'll think this is. What we talked about before today is critical numbers are when the first derivative is 0 or undefined. They might be extrema, relative extrema. They're not guaranteed to be, but if it makes the first derivative 0 or undefined, it's considered a critical number, period. End of definition. A point of inflection has two parts. It almost sounds the same. It's not where the first derivative is 0 or undefined. It's where the second derivative is 0 or undefined. And this is important, because unlike critical numbers don't have to be relative extrema to all of a sudden be critical numbers. A point of inflection has to have this happen, and concavity has to change. So it changes from concave up to concave down, or concave down to concave up. So this in red helps you find potential inflection points, but you actually have to make sure that the concavity changes before you can call it an inflection point. Okay, so if I know that this graph might be changing directions when the second derivative is 0 or undefined, you need to solve. This one solves with factoring. Looks like -2 and +2 are possibilities. X equals 2, x equals -2. Now I'm doing another sign chart, but I'm not using a sign chart for increasing, decreasing. You could do that as well, but that's not what this question's asking for. I found the two potential inflection points. So I like to call these PPI for possible point of inflection. You need to know that that's not a real math acronym, but it is super important that you understand these are not inflection points yet. They're potential or possible inflection points. You actually have to see what the concavity is going on in here. So plug in some number between -2 and 2. Now, this is where all this information does start to pile on a little bit. You need to keep straight that if you want a point, you plug it into the function. If you want to know the slope at a certain x value, you plug it into the derivative. And if you want to know the concavity at a certain x value, you need to plug it into the second derivative. Depends on what you want, depends on what you should plug it into. So if I plug 0 into the second derivative, it is negative, which means it is concave down. So if you just make a little piece that looks like it's concave down, you can remember that's what it's doing during that time. But since this is potentially an inflection point, it could potentially be changing concavity here. So don't plug in 2 into the second derivative. 2 makes the second derivative 0. That doesn't tell us anything. We need to figure out what's going on over here. So plug in anything bigger than 2, something easy like maybe 3. If you want concavity, plug it into the second derivative. Plugging in 3, I don't know what that is, but I know enough to know that it's positive. When the second derivative is positive, it's concave up. Now, this isn't important for this question, but now I can see it's switching concavity, concave down to concave up. So now it's no longer a potential inflection point, it is an inflection point, or point of inflection. To know over here, just got to test it as well. Try plugging in -3 into the derivative, you get something positive. You have to memorize when the second derivative is positive, it's concave up. And if there's a point where the concavity is changing, then it's no longer a potential inflection point. He actually is an inflection point. So all of that, so that I can actually answer the question now. I can say, here is where he is concave upward. It was from this time, -infinity to -2, and during this time 2 to infinity. It's kind of like the sign chart where we did increasing, decreasing. This doesn't count as any justification, but it makes it painfully obvious where it's concave up and concave down, assuming that you don't have a mistake. Okay, and then it says tell where the intervals of concavity, so I also need to say concave downward locations. And that would be -2 to 2. So critical numbers are where first derivative is 0 or undefined. Inflection points occur when the second derivative is 0 or undefined, but it also has to change concavity. Plugging numbers into the first derivative tells you what the slope is, so you know if it's increasing or decreasing. Plugging numbers into the second derivative tell you whether it's concave up or concave down, which tell you about concavity. Now, one of the trickiest things about these is that you might want to highlight here. When this says point of inflection, point implies that there is it's a point on the function. I know that sounds basic, but sometimes concavity could be changing. But if x equals 2 did not exist here, then it's not even a point, and if it's not a point, we couldn't call it a point of inflection. So, okay, so before we keep going, kind of like the stuff we've been doing, I'm trying not to compare and contrast too much, but you will certainly have a question like this on your test where we'll ask you to find where it's concave up or concave down, or both. You will have questions about inflection points. So 2 separate questions in there, and they kind of tie together. Okay, on to the next page. 2 common mistakes when finding a point of inflection. Assuming that because the second derivative is 0, it means there's a point of inflection. Just because the second derivative equals 0 somewhere does not guarantee that the concavity is changing. Okay, the second common mistake is assuming that if the second derivative is undefined, means that there's not a point of inflection. Points of inflection could occur when the second derivative is 0 or undefined. The undefined is one that you almost never use, but it does get tested, so you have to say that in your head that way each time. Okay, so today we are focused on the concavity, or at least for a little while here. So we need to pay attention to what type of graph we have. Question 2 says here's a derivative graph, and it wants us to state the intervals of concavity. So we should be able to say when he is concave down and when he is concave up, or downward and upward, whatever. But they're not giving me the second derivative, they're giving me the first derivative. So if I have information about the first derivative, what about the first derivative tells me something about the second derivative? Right, slope is like derivative, so if you want the derivative of the derivative, you want the slope of the derivative. So when the slope is negative, aka the first derivative is decreasing, we wrote this in our notes just on the front page. When the slope is negative, that means the second derivative is negative, and when the second derivative is negative, is that concave up or concave down?
Concave down.
That's correct. So that looks like from -4 to 1, -1, and from 1 to 2. Again, we are not talking about the concavity of this graph. We're talking about the concavity of the second derivative given first derivative information. Okay, same thing with concave up. You'll have to memorize that that's where the second derivative is positive, which is the same thing as saying the first derivative has a positive slope, aka the first derivative is increasing. So that is from -1 to 1 and 2 to 3. So I don't think you should be thinking or trying to memorize that it's concave down when the graph is decreasing and concave up when the graph is increasing, because it depends on what type of graph you're talking about. Memorize that derivative means slope. Realize if you want information about the second derivative, you should be thinking about the slope of the first derivative. And then you're not memorizing anything new. Okay, so question 3. Why is...
Wait, we didn't do the, did we do the concavity? Like the, okay.
Yeah, it's right there.
What about the points of inflection? Wait,
Oh, yeah, I'm sorry, points of inflection. So anywhere that's a point, which we actually don't know, but that we would assume it, and the concavity is changing. So here, here, and here. Or you can see at -1, it stops being concave down and starts being concave up. At +1, it stops being concave up and starts being concave down. And at x = 2, it stops being concave down and starts being concave up. So you should be able to see that here and or here. But thank you. I just didn't read the directions very well. X = -1, +1, and +2. Okay, so if you don't take my advice and you just memorize, well, when the graph's going down, that's concave down, and you say it's concave downward from -infinity to -2 and 2 to infinity, why is that not correct this time? Right, they're not giving us the first derivative, they're giving us the second derivative. So if you're just trying to memorize way to get to the answers, I mean, more power to you, I guess, but you're going to memorize a lot more than the rest of us. It's concave down when the second derivative is negative, and since this is the second derivative, he is negative when he's below the x-axis. And he is concave upward when the second derivative is positive. And if you're looking at a second derivative graph, you have positive values when you're above the x-axis. So that's where it would be concave up. All right, anything you want to ask about that?
points of inflection just be where X is 0? Or
Yeah, I'm sorry. I need to be reading the directions before I assume that. Points of inflection would be anywhere where it's changing direction. So if you do like I do and color it, then it's really easy to see. Concave up, concave down, point of inflection. Concave down, concave up, point of inflection. Concave up, concave down, point of inflection. The inflection points are at x equals -3, 1, and 3. But that's only because it's a second derivative graph. It doesn't mean x-intercepts are always the inflection points. Please try not to take shortcuts. Okay, now we're okay. This is a little bit of a sidebar, but it came up with concavity, and I don't remember which question somebody had yesterday about it. So I can't give you their question, but I know this happens a lot. If you guys did this with increasing, decreasing, like we've been doing, and you find the critical numbers, blah, 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 and then you test here, it's increasing, increasing. When would you say this graph is increasing?
Always.
Like this? That's not correct, and that's what I'm worried about. It's increasing until 0, but it's not increasing at 0. At 0, he has, if he's a critical number, he's horizontal for that instant. And he increases after. He's not actually increasing at 0, so you need to split it up into 2 segments like this. So, kind of unrelated, but they do throw that at you sometimes, so it's good for y'all to be aware of that. Okay, okay, so we've got one more kind of unusual question here, but it shows you some of the stuff that you'll get to eventually, and then we'll start over and do a few easy questions. Okay, does the tangent line to this graph at x equals 1 lie above or below the graph of f? All right, so you're not going to understand why I'm doing this yet, but I'll draw a picture so you can see why I'm doing this. I am going to figure out what is the concavity of this graph at x equals 1. So to do that, I need the second derivative, which means I need the first derivative. The first derivative is going to require product rule and some chain rule. Derivative of x with e to the negative x left alone, plus x times the derivative of e to the negative x left alone. You getting this down? And then the second derivative, derivative of e to something is e to something, but chain rule. This part would need product rule also. Derivative of x with this left alone, plus x left alone times the derivative of this. So just like our last section, I can't make derivatives or solving these for 0 and undefined any easier other than extra practice. But the good news is it should be getting easier because product rule, quotient rule, chain rule, power rule, and the ones you memorize are the only ones you ever have to do. So okay, so now I've got the second derivative, and I want to figure out what's the concavity at x equals 1. So if I plug 1 into the second derivative, I get e to the negative 1 times a negative minus e to the negative 1, just like 1 over e, plus 1 times e to the negative 1. So it looks like those two cancel, and honestly I don't really care too much other than to see at x equals 1 the second derivative is negative. Now, since the second derivative is negative, what do I know about the function at x equals 1?
It's concaving downward.
Okay, so x equals 1, I have no idea what this graph looks like, but I believe he is opening downward, concave down. So now back to the question and how I knew to do this. It says, does the tangent line at x equals 1, so here's x equals 1. If I draw the tangent line, does the point okay, well, I maybe shouldn't have. This is concave down more than just x equals 1. But do you see how, since this is concave down, it's turning downwards. So this point lies above the graph of f. Here's where f is, the function, but the tangent line is above it. And I know that because it's turning downwards, and I know it's turning downwards because the concavity is negative. The only other thing that could have happened is it could have been concave upward, and in that case, the tangent line is way down here, whereas the function is up here, and the tangent line would be below. So if you care about the tangent line being above or below the function, you're actually thinking about concavity, because concavity is either turning away from it, going further down, or away from it, further up. So sometimes if you just make a quick little sketch, again, it doesn't have to be anything complicated. Concave up, tangent line, below the function. Concave up, tangent line is above the function. That's why you care about concavity, about where it lands, because you know which direction the graph is turning. So that's why I did all that, and
So is the answer above or below the graph?
well, since it's concave down, the graph is turning down over time, whereas the tangent line is linear, so it's above. This point's above where the function would be. Again, you don't need any super accurate graph or anything to be able to say that, but if it asked you if it was above or below, that's how you're supposed to figure it out, and then your justification would be is concave down or concave up, because the second derivative is positive or negative. Okay, so that's kind of a weird question to give you this early, but that's okay. So resetting, so we're back to the practice now. As you should know, on these type of worksheets, the practice usually starts you off not too bad and then builds up in difficulty. So again, we're not going to do the whole thing of this today, but I do want you to get some practice in and hopefully get a decent grasp of what you should be doing. So this question gives you a table. The table gives you some x values, some intervals, and its corresponding second derivative, whether it's positive, 0, or negative. And from that, you should be able to state where the function is concave up, concave down, and if there's any point of inflections and what they are. So now I want you to try to answer that from the graph, please. Okay, that one shouldn't have been too bad. So when the function is concave up, it's when his second derivative is positive. That's the thing you have to memorize. Well, when the second derivative is positive is during this interval. That's all you needed. Likewise, to know when it's concave down, you have to memorize that is when his second derivative is negative. Table's telling you it's negative during these times. So that's the second answer. And where there is concavity changing at a point, was going from concave up to concave down at x equals -1/2. So that's a point of inflection. It's it's not x equals 0, that's its value, it's concave, or it's changing concavity when x is negative 1/2. Okay, you guys get all three of those? Okay, so most of the time, as you guys know, sometimes you get the table, and honestly, tables can be tricky because a lot of times there's a lot of extra information, but that's what you would be looking for. But most of the time it's going to be like this. Here's a function, find the concavity or find the points of inflection. It's all basically the same work anyway. So let's do question 2 together, and then I will let you try on question 3 before we go over it. So inflection points, you have to have this memorized. It occur when the second derivative is 0 or undefined and the concavity has to change. So 0 or undefined means I need to be able to take the first derivative so that I can take the second derivative. I know the inflection points are going to either happen when the second derivative is undefined, which is not this question, or 0. So we can multiply both sides by -2 to make this look a little bit nicer. But then I need to think of what values of x divided by 2 would give me a sine of 0. So instead of doing that, which is a little bit harder to do in my head, I'm going to think about what values of sine give me 0. So sine of 0 at 0, well, actually it says negative pi to 3 pi. So at negative pi sine of 0, at 0 sine of 0, at pi at 0, at 2 pi at 0, and at 3 pi at 0. That's all the times, if you keep going, between negative pi and 3 pi that sine is 0. But that is if it was sine x, not sine of x over 2. So to go from x over 2 equals these values to just x, we can multiply everything by 2. So the ones that fall in this range, negative pi to 3 pi, would just be these two, 0 and 2 pi. So those are the two places it's likely to be changing concavity, not a guarantee. So I'd make a sign chart. X equals 0 is a potential point of inflection. X equals 2 pi is a potential point of inflection. Again, this is not a real acronym. It's just, I'm trying to emphasize that we don't know it's an inflection point yet. Okay, and so if these are the two places concavity might be changing, I need to check around those two. So I need to check these 3 places. So plug in something here, like pi, into the second derivative, if you want concavity. So the sine of pi over 2 is 1, times negative 1/2 is negative, so concave down. Test something bigger than 2 pi, but less than 3 pi technically. So whatever you think is going to be easiest here. I would do, I don't know, I'll do 5 pi over 2. I think that's 2.5 pi.
The middle point, is less than 0?
Yes. Okay, at 5 pi over 2, if I plug that in, oh wait, I need to plug it into the second derivative. 5 pi over 2 divided by 2 would be 5 pi over 4. The sign at pi over 4 is something negative. A negative times a negative is positive. When the second derivative is positive, it's concave up. So this is similar to those increasing, decreasing symbols or sign chart, just that, you know, instead of it going up or down, I care about if it opens up or opens down. Instead of me testing first derivative values, I'm testing second derivative values. Okay, and then finally, I need to test something less than 0, but not negative pi or left of that, so I don't know. I'll try negative half a pi. You can plug in whatever you want as long as it's in the right range there. Plug it into the second derivative, you would get negative pi over 4. The sign at negative pi over 4 is negative. A negative times a negative is positive. Again, it's nice that I don't actually care what the value is. Just be careful that you're keeping up whether it's positive or negative. Okay, so now I can finally see that at x equals 0, it's changing concavity, concave up to concave down. And at x equals 2 pi, it's changing concavity. It's changing from concave down to concave up. Those x values, the points of inflection, are where that concavity changes. Yeah.
Wouldn't the second derivative negative 1/4 sine of the 2 is a chain rule?
Yes, you're right. Thank you. I forgot to do the chain rule the second time. The good news is that doesn't mess anything up for us because this is still negative, so I was still trying to figure out if this was positive or negative, so it didn't mess us up, thankfully. But kind of like the first derivative test where you have to do all of the work to find relative maxes and mins, but then if you needed to say where it's concave up or concave down, at least you've already got that done. Just like first derivative test, you know where it's increasing and decreasing. Okay, so finish copying that down and then give number 3 a shot. I'd like you to see where you get stuck or if you're able to potentially finish one on your own now. Now, of course, number 3 is a little bit harder. It looks harder than 4 and 5 just because of its function, but the process should still be the same. So I'll give you a few minutes head start and then let's make sure you do that right. Let's see. Okay, let's see how you did. Okay, so everything we are looking at new today revolves around second derivative. So this derivative is just a little bit harder, but first derivative, e to something is e to something, and then chain rule. I pulled the -2 out. That was just what I thought was better, but then for this part, you have to do product rule. It's x times e to the -x squared. So I had to do product rule for all of that. And if I'm trying to figure out where this is 0 or undefined, personally, I would pull out a GCF. Both of these two terms had this e to this stuff, so I could pull it out front. So I don't think this will ever be undefined, but it certainly should be 0. So I could set this factor equal to 0, and I can set this factor equal to 0. And again, this is the other part of the problems that just are going to vary in difficulty. Okay, that side never happens. E to the -2x never equals 0. But over here, subtract the 1, divide by -2, take the square root. And what is the square root of a half? What times what gives you a half? Okay, good. That's sorry. That doesn't simplify, so that's good. But I still had a mistake here. That's what I meant to ask. What did I? You started doing your sign chart, and did you only test the square root of 1/2? Right. When you take the square root of both sides, you've got to do plus or minus, and that was one thing on the last test that was on the FRQ at the end of the question. You had to take the square root of both sides, and if you didn't remember plus or minus, you didn't get the right answer and you lost a point. So I know you've heard that for a long time, but these are the two places that might be inflection points, possible points of inflection, but only one requirement's been met so far. Those are the two times your second derivative was 0. But the other requirement is that the concavity is changing. So test something in the middle of these two, like 0. Since I care about concavity, I would be plugging into the second derivative. You can plug into the second derivative here or wherever that you think is easiest. But this would be a negative times a positive times a positive. Negative, positive, positive is negative, which means it's concave down. You need to try something bigger than the square root of 1/2. So if you're not sure how big that is, pick something that you're sure is bigger. Pick 10. Doesn't really matter, as long as it's something we can keep up with in our head. So if I plug 10 into the second derivative, I get a negative times a positive times a negative. Negative times negative would be positive, which is concave up. And then since he might be changing concavity here, I need to test something over on this side. So again, if you're not exactly sure how big the square root of 1/2 is, just pick something that you know is less than that, like -10. Negative, positive, negative is positive. So if this question asks you to find where's concave up, your answers are here and here. If it asks you where's concave down, it's right during this time. If it wants both, then you've got both. And if it wants points of inflection, well, it's changing concavity at this x value, and it's changing concavity at that x value. This one plus or minus the square root of 1/2. That's where it's changing concavity. So whether you want to know the concavity or you're trying to find the points of inflection, your work is all basically the same. You pretty much need to make this sign chart to visualize what's going on. Now again, the derivative and solving the derivative for 0 or undefined are the two things that can vary per question and be harder, but the rest of it should be pretty formulaic. You need the second derivative, you need to know where the second derivative 0 or undefined, define potential inflection points. Once you actually see the concavities changing, they're no longer potential points of inflection, they are actual inflection points. Okay, so try that again for question 4, please. Number 4 should be quite a bit easier, I think, just because the function's easier to work with. But you should certainly make it further than you did in question 3. So try that for me. We're going to go through at least question 40. I'd like to do 2 more on this worksheet with you. 4 and then 5, and then we'll call it quits on this worksheet for today. And then I'll ask you to finish up the last one. Okay, is that what you got for the second derivative? Of course, there's lots of chain rule in there. Chain rule on the first one, and then you had to do product rule for the second derivative. And then I combine like terms. Okay, so you should have done that to find the second derivative. It said each factor of the second derivative equal to 0. It looks like the square root of 5/6, but make sure you did plus or minus. It's going to be extra confusing if you only get one of those two. So the square root of 5/6 is a potential point of inflection, and the negative square root of 5/6 is another potential inflection point. Those are the two places you should be testing to see if one or both of those is your answer. So maybe plug in 0 into the second derivative. You get a positive times a negative, which is negative, concave down. Maybe plug in something like 2 into the second derivative, something bigger than the square root of 5/6. Again, if you don't know how big the square root of 5/6 is, just make sure you're picking something bigger. That would be a positive times a positive, which is positive. Second derivative is positive, it's concave up. Repeat one more time. I'll try -2, I guess. That would be a positive times a positive, which is positive. Now, if you wanted to know where it's concave up or concave down, all that information is right there in front of me. But this particular question was asking about inflection points. I now know that those are not potential inflection points, but actual inflection points, because it's switching from concave up to concave down, and concave down to concave up. So I would say plus or minus the square root of 5/6 would be the two places where concavity is changing. Okay, let's do one more for today, and then we'll save a couple for next time. Again, I like for you guys to save a few, because if you have to think about it all again, then it helps stick in your brain a little better. Okay, let's make sure you did that one right, or at least take some notes about what went off. Okay, so points of inflection are where concavity changes. Concavity is determined by the second derivative. So power rule for first derivative. Power rule for the second derivative. Looks good. Okay. You got to think about where this is 0 or undefined. I know the undefined does not apply most of the times, but it will apply sometimes. So this would be only where x equals 0. X equals 0 is the only place it might change concavity, which is what we call an inflection point. But you're not allowed to call it an inflection point until you're sure concavity is changing. So, test the concavity to the right of 0. It's something positive, so I know he's concave upwards after 0. Test something to the left of 0, which is also positive. So, did you get that it was concave up here? So if the question, before we talk about inflection point, if the question was, when is this concave upward, what would you say?
Negative infinity to infinity.
Okay.
0.
That one does not count. Because if you do this, you're including 0. At 0, it's not concave up. At 0, it's 0. It's not doing anything.
Negative infinity, 0, union, 0 to infinity.
Right, which is just a fancy way to say everything from negative infinity to positive infinity, but numbers less than 0 and more than 0. So basically skip 0. So again, I don't know if that comes up on our next test, but I know it does show up eventually. Okay, so concavity is not changing, so I would say no inflection points. That's what y'all got? Okay. And just one last connection here. So you should not be doing this to get your answer, but if you feel like you're struggling with what you're trying to find, and if your answer's correct, you're just trying to reason through it and make sense out of it. One thing that you could do when you go back and finish this worksheet next time is you could graph the function. You can see how the function is, it's always concave up, it's never concave down, so concavity never changes, which means that there's no inflection points, and then you could feel better about your answer. But don't rely on that as a way to find your answer. So, just like the first derivative is great about finding increasing, decreasing segments, the second derivative is good at finding concave up, concave down segments. First derivative is where the zero undefined gives you critical numbers, and the second derivative, zero or undefined, you might have inflection points. So, very similar sounding things, but the small differences are important. So, is there anything you would like to ask about this today before we put this one up? Anything you'd like to clear up about this topic? Okay, then I would like to ask you to finish up the one from last time. And so I will give you what was that, 42? So assignment 42 is the one I will ask you to turn in on Thursday, or in Google Classroom if you want to do it early. So this is the one you need to finish. You don't have to do anything else on assignment 43 at this time. So this was about finding not relative max and mins, but absolute max and mins, which is a process called extreme value theorem. Extreme value theorem just told you that the absolute max and min are either going to occur at critical numbers or endpoints. So basically we found the critical numbers, tested the critical numbers, tested the endpoints, and the absolute max and absolute min had to be in that list. This table is what we call the candidates test. So you need to make sure that you're making the candidates test each time. But that is the quickest way and easiest way to find relative maxes and mins without a calculator. So again, I think you've got about, you guys got a little further on this worksheet than my other classes. So you should be on question 5. Yeah, there's like 8 or 9 questions, it looks like. So if you need help, please let me know. It's your last class time to work on extreme value theorem and candidates test. Harper, what do you need?
I'm just like, you know, something sad.
Well, now's not the time for that.
Oh, yeah, I think there was more.
Well, if you find it, let me know.
Oh, I have it.
I have 3 homework papers with no name on it. One is a book assignment that was on graph paper. One was the worksheet that was in a lot of red pen. And another one was an assignment 40 that was in pencil. So I'm gonna pass these back, but if you don't get yours back and you think those are yours, you just need to come claim them. If I switched your seats now, I second guess myself. I knew this one was you because you had your name on it. I assumed this was you because it was.
Yes.
Figured out how to use this guy yet.
For the most part.
Your fan club was outside now again.
Who's that?
No, okay. I took test today on the AP classroom, and I think you're still not signed up for it. Okay, I'm just letting you know.
I
because
just forgot to do it, I'll do it,
it doesn't matter to me, I'm just telling you that once, I don't know when that deadline is, but it's like a week or so. Once that hits, there's nothing I can do to help.
This is not gonna be.
That's 90. be a lot more parts that where it leads to 77 comes in. We're still missing something. Let me double check it. We already told you didn't sign up for.
Yeah.
Okay. Okay, so the same thing I was telling him, there's a deadline that the school sends off to order you an AP exam, and once that deadline hits, they're not gonna do to help, so. It's not gonna upset me if you don't, but I just want you to know that that happens. Oh, thanks. One second.
So number 5. Would it be like you bring the 2 down here?
Let's see. You're gonna have to do product rule. This is X times some stuff. You gotta do product rule.
Okay. Is that right?
Well, I would take the derivative of X first, which would just be 1, times this left alone. You could do it any other way, and that would have been fine. Okay, that looks good. There's your first derivative. So now you got to try to figure out where that's 0 and undefined. So maybe you could factor out a e to the 2x since they both have that.
I got it from there. I just wanted to make sure I had the first derivatives right.
One assignment 40 that was not claimed, so I'll put it in the homework box. If at some point you realize that you turned it in and didn't get any points for it, you might go check it to see if it was yours. Yep. You keep the 2. It's just like, if I asked you what's the derivative of 2x squared, you would bring the power down and lower the power by 1. You wouldn't say that this is 0, so 0 times that becomes 0.
I did not have it from there.
Okay. So you're trying to find critical numbers. You already have the endpoints. So critical numbers are where the first derivative is 0 or undefined. So set that equal to 0. And then you need to solve that. So I would solve with factoring. I would do a GCF. They both have an e to the 2x that you could factor out.
Oh, so
That one should be a 2x, e to the 2x. Okay.
And
Now
you
set each
divide.
factor. Now set each factor equal to 0. Just like in algebra, if you have x plus 1 times x plus 2 equals 0, you can set x plus 1 to 0 and x plus 2 equals to 0. Yeah, that one never equals 0, but the other one will. So, correct. So the only critical number is -1. So you need to test that and the endpoints, and then your two answers should be there. Okay, guys, we're down to about 8 minutes here. So let me remind you of the directions. The only assignment that you have, I know on the agenda it says finish 43, but that was just if you had time to get to it. The only assignment I will be taking up on Thursday is assignment 42. Before I change it over to the daily puzzle here, I know we've got another test coming up in a few classes, I guess, but y'all need to understand you have seen most of the important stuff. By the time there's at least a question, at least one question on finding critical numbers, at least one question on finding inflection points, at least one question finding concavity intervals, at least one question finding increasing, decreasing intervals, at least one question finding relative maxes and mins, at least one question finding absolute max and mins. You do that and you already know what most of the test is going to look like. So, something to keep in mind. So, I guess if you're feeling like you're falling behind, you need to start putting in a little extra effort. Don't wait until the test time. Do that. Okay, as far as our puzzle for today, okay, I'm pretty sure you solved this one. Okay, did you do the eye test?
Yes.
Okay, did you get this one? Okay. Have to try to find the 4 numbers that make all of that true. I don't share the answer to this one because once you know the answer, you can check it yourself. So. I also mentioned last week that I knew the heat would be out next week or last week, and it was supposed to be fixed. It's obviously not fixed. They're now saying it's supposed to be fixed sometime this week. So I wouldn't hold your breath. Might bring a blanket or a hoodie or something. I don't know when they'll have it fixed. I thought the back of your hoodie was gonna have the rest of your phone number on it. Nobody's figured it out yet? You did? Alright, what do you think the top left is? 1. Okay, top right?
15.
Okay, 1 times 15 is 15. What's the bottom left?
2.
Okay, 1 plus 2 is 3. And then bottom right?
Negative. Or negative.
2 minus negative 3 would be negative 5.
That would be minus of minuses.
Yeah. What was your top right number?
15.
Oh, and then 15 plus negative 3 gives you 12. That sounds right. I'm guessing you just guessed and checked your way to the answer? How could you do it mathematically if you couldn't figure it out, guess and check? Oh, come on.
You said some equations equal to each other?
Yeah, just make the top left box be A, the top right box be B, C, D, and you got 4 equations. A times B is 15, A plus C is 3, C minus D is 5. 4 equations, 4 unknowns. If you know how to do matrices in your calculator can solve it for you.